Amid the vastness of the cosmos, the Milky Way stands out by hosting a colossal number of stars. Estimates range from 100 to 400 billion. Imagine if each of these celestial lights had at least one planet orbiting them. This idea leads us to picture a cosmic neighborhood filled with up to 400 billion worlds, or even more. Now, extend that scenario to the entire universe, where trillions of galaxies stretch across space, and the total number of stars becomes almost unimaginable. Some researchers even claim there are more stars scattered throughout the cosmos than grains of sand on all the Earth's beaches. If each star hosts a planet, the universe transforms into a true repository of fascinating worlds, brimming with unique potential and surprising stories waiting to be discovered. Yet something paradoxical emerges in this vast setting. Even with the enormous number of planets, we have not yet received any message from extraterrestrial civilizations. No intergalactic hello, no sign of alien life, absolutely nothing. This enigma, where the odds of life seem high yet there is no evidence of contact, is known as the Fermi paradox. This dilemma prompts the scientific community to question whether life is truly rare or if our own location and methods of observation are limiting us. A key clue to unraveling this mystery might be closer than we think, right in our own cosmic neighborhood. Recent studies have revealed that the Milky Way is strategically positioned near the heart of a vast void known as KBC, which extends for about 2 billion light-years. This discovery challenges some basic concepts of cosmology, since a space so devoid of galaxies raises new questions about the Big Bang, the distribution of galaxies, and the mechanisms governing the expansion of the universe. By delving deeper into this phenomenon, scientists suggest that the KBC void could be the key to solving two of astronomy's greatest mysteries: the Hubble tension and the Fermi paradox. The detection of the KBC void became possible thanks to the creation of three-dimensional maps that detail the distribution of galaxies in the nearby universe. Scientists like Keenan, Barger, and Cowie used surveys that measure redshift, an effect that stretches the light of galaxies due to the expansion of the universe, to identify a region with a much lower concentration of galaxies than expected. This region turned out to be about 7 times larger than a typical cosmic void, which initially sparked significant skepticism in the community, as the existence of such an empty space challenges both the cosmological principle of uniformity and the predictions of simulations based on the Lambda CDM model. As new observations were made, the existence of this vast void became undeniable. Various telescopes and surveys confirmed the extreme scarcity of galaxies in this 2 billion light-year region. Rather than being seen as a problem, scientists began to consider that this void might be the key to resolving the Hubble tension, a mystery that has puzzled astronomers for over 60 years. The Hubble tension refers to the discrepancy found between the two main methodologies used to measure the rate at which the universe is expanding. Since the Big Bang, the cosmos has been expanding, and this rate is expressed by a number known as the Hubble constant. A direct approach, based on observing nearby galaxies through variable stars and supernova, suggests that the constant is around 73 kilometers per second per megaparsec, meaning that for every 3.26 million light-years, a galaxy's recession speed increases by approximately 71 kilometers per second. In contrast, the indirect method, which analyzes the cosmic microwave background, an echo of the Big Bang permeating all of space, estimates a value of about 67 kilometers per second per megaparsec. Although this difference might seem small, it is statistically significant and implies roughly a 10% variation in the measured value. This discrepancy is not just a numerical curiosity. It has deep implications for the estimated age of the universe. If the expansion is indeed faster, the universe would be around 12.5 billion years old. If it is slower, its age would be closer to 13.8 billion years. This 10% difference raises doubts about the accuracy of the current cosmological model and suggests that unknown factors, possibly involving dark matter, dark energy, or even modifications to gravity, could be at play. An intriguing explanation for this tension comes from our own location in the universe. We live within the KBC void, a region with a matter density about 20% lower than the average observed on larger scales. This lower concentration of matter means that the local gravitational force is reduced, while denser areas around it exert a greater pull, drawing everything out of the void. This phenomenon might create an illusion, making local measurements of the universe's expansion rate appear about 11% higher than the true value. The universe may not be accelerating as much as we think. What we observe is partly an effect of our privileged position in a low-density area, influenced by the gravitational forces of nearby galaxies. This new perspective not only broadens our understanding of cosmic dynamics, but also reinforces the importance of considering the local context when interpreting large-scale measurements. The interplay between regions of different densities and the gravitational influence of these areas may be fundamental in resolving mysteries that, at first glance, seem contradictory. Thus, as science continues to explore and map the far reaches of the universe, discoveries like the KBC void remind us that the cosmos still holds surprising secrets and that our understanding of it is always evolving. The existence of the KBC void is seen as a crucial piece in solving the Hubble tension enigma, but at the same time, it challenges the Lambda-CDM model, which has long been the favorite among modern cosmologists. This model is based on the density fluctuations of the early universe and the idea of a relatively uniform matter distribution on larger scales. However, it fails to explain the formation of regions as empty of galaxies as the KBC void. To work around this limitation, researchers have adjusted the initial conditions of fluctuations and intensified structure formation processes in their simulations, even reproducing voids similar to the KBC. Yet, these adjustments resulted in numbers and patterns that deviated from the predictions established by Lambda-CDM. Faced with this inconsistency, some scientists turned to an alternative theory called modified Newtonian dynamics, or MOND. Instead of introducing as yet unidentified dark matter to explain the observed anomalies, MOND proposes a revision of Newton's own laws of gravity, especially in situations of low acceleration. According to this approach, the growth of galaxies and clusters would occur more rapidly than predicted by the Lambda-CDM model, making the formation of large cosmic voids more common in a universe governed by these new rules. The dilemma arises because, while some observations of the universe seem to favor the explanation offered by MOND, other evidence continues to support the Lambda-CDM model, leaving the scientific community in a kind of tug-of-war without a definitive consensus. The discovery of the KBC void, therefore, forces us to rethink or even reconsider some of the fundamental principles of modern cosmology. If the universe shows significant variations in matter density, as is the case with regions devoid of galaxies, similar to our cosmic neighborhood, it may be necessary to reevaluate key concepts related to dark energy and the mechanisms of forming large cosmic structures. Moreover, this peculiarity also casts new light on the famous Fermi paradox, which asks, if the universe is so vast and filled with stars, where are the aliens? When analyzing the KBC void through the lens of the Fermi paradox, 3 points stand out. The first is isolation. This region shows a scarcity of galaxies and, consequently, stars. If life tends to develop in denser areas with a greater supply of resources, perhaps we are located in a true cosmic dead zone, which would make the emergence and detection of other civilizations more difficult. The second aspect is the vast distances. Even if advanced civilizations exist nearby, the extreme dispersion of galaxies within the void implies that any form of interstellar communication would be extraordinarily slow. Finally, there is the hypothesis that more advanced civilizations might deliberately avoid contact with less developed societies, an idea reminiscent of the dark forest hypothesis. This combination of factors may partly explain why, despite high theoretical probabilities, there has been no unequivocal sign of extraterrestrial life. In addition to these points, the characteristics of the KBC void might both favor and inhibit the emergence of life. On one hand, if life tends to develop in environments richer in matter, our isolated location could reduce the chances of interaction between civilizations. On the other hand, densely populated regions of galaxies may also be the stage for extreme phenomena, such as supernova explosions and intense quasar activity, which could be devastating to any attempt at biological development. This duality raises an intriguing question. Could our existence in a cosmic desert have in some way been a protective factor, allowing life to establish itself without the interference of catastrophic events? Finally, this discussion also extends to anthropological questions. The anthropic principle, which suggests that the universe appears as it does because we are here to observe it, gains a new dimension when we consider the KBC void. The low density in this region may not be just a coincidence, but a key element for the ideal conditions for life to emerge. If the universe were homogeneous or lacked large voids, the conditions for life's development could be drastically different, perhaps even impossible. Even though the anthropic principle continues to be debated, with many viewing it more as a philosophical reflection than a rigorously testable hypothesis, the KBC void adds another layer of mystery to our understanding of the cosmos and our place within it. As the scientific community continues to uncover the secrets of the universe and test innovative hypotheses, the definitive answer regarding the role of the KBC void in resolving the Hubble tension, and consequently, in understanding the great cosmic mysteries, remains shrouded in uncertainty. This enigma challenges us to rethink traditional concepts and drives us to develop new methodologies, combining sophisticated calculations with high-precision observations. Every new discovery, no matter how subtle, brings us closer to a clearer view of how the universe operates, revealing layers of complexity we had never imagined. Thus, the path to unraveling this mystery demands time, dedication, and inevitably, the emergence of revolutionary ideas that may transform our understanding of the cosmos. Given the vastness of the universe, with its infinity of galaxies, stars, and planets, how can we understand that even under seemingly favorable conditions for life, we have still not detected clear signs of extraterrestrial civilizations? Could factors such as our location in a cosmic desert, or variations in the distribution of matter significantly influence the emergence and sustainability of life in other corners of the cosmos? Share your thoughts in the comments. Are we alone in the universe, or just far away from everyone else? If you love the mysteries of the universe, feel free to subscribe to the channel, like this video, and turn on notifications. That way, you won't miss any news about our space journey and the advances that take us ever farther. Thanks for watching. See you on the next trip.